Okay.
Okay, it's okay.
Please.
So, good morning. My name is Yunlong Chi. I'm from the IHEB. So it is my pleasure to give us some accelerator summary for this workshop. Through the 2 days, we have about 25 talks, including the 3 plenary and about 22 parallel. This talk says we covered the 2 circular collider, it's a CPC and FCC, and the 2 linear collider, it's IRC and the CLIC. So this is presented as the CPC CDR parameters. So we have mainly first is focus on Higgs factory. And this one is the FCC collider, the parameters. It's first focusing on the J factory. So this is the linear collider design parameters. So IRC as now is going to is 250, and we have in the future it will be 500 GV, and the CLIC is 380, and the future is 3 TeV. This is the time schedule for the 4 colliders. The CPC is start construction is about 2022, and the FCC is planned to start is about 2028, and the IRC will be maybe make a decision in this year, and where is to construction, and this is a collocated roadmap. It's where construction is planned to start as 2030s. 2035, okay, 2025. So this is a CPC, SPPC is now is the almost is to completed is the CDR. CDR will be as printed before end of this month, and just this month. So this is generally the layout of the CPC tunnel. Yesterday, as presented by Yu Xiao. So this is some tunnel schematics and some the surface the infrastructures for the some buildings. And this is collider ring tunnel, and as a shelter auxiliary is the tunnel as a schematics. And this shows some IP, the tunnel, and some the detector as the locations. So this is some preliminary as the CPC SPPC tunnel as the classification. This is the associated tunnel classification at the arc section. As the device is about 6 meters, and this is a main ring, this is a booster ring. This is in the future the SPPC. And this is for the tunnel cross-section at the RF section. This is one, the FCC tunnel integration in the arc. The circumference is about 5 meters. And for the machine is designing, there's first is the CATIA as a melody as presented is using a crab waste is the method for the high luminosity as a machine designs. This is some examples for the Daphne and the Colloid 2 as the machines. And the crab waste collision scheme is implemented for the first time, which is a large accelerator, including a strong solenoid field. The crab waste collision scheme has proven to be a viable approach to increase luminosity in circular colliders. So, and for Seki as nicotine is to presented the J-pole as a polarization as a schemes. This is for the preliminary designing for the CPC J-pole as a polarization. And some tracking-based method to calculate the F. So It is possible to reach the polarization in the range and 60 to 10% in 45 GB in the CPC in time of the 2 to 4 hours using. This is left chap that presented as the electron source for the FCCEE. The FCCEE requires the electron sources are very high as a charge and very low as the normalized injection emitters. So they get the new ideas for the EGAN design and the cathode materials are required. Suggestions as to using RF gun as basically the parallel coupled accelerating structures. They developed this prototype of this structure. Design of this structure allows us using internal permanent focusing magnet. So the design of a parallel coupled accelerating structure using permanent focusing magnet and created a strong magnetic field along the cavities and save the beam size. There's a plan now is to stress test with the cathode and using it measuring of the quantum efficiency of the cathode and RF can is the production. This one is presented by Zihou Bai at Tsinghua University for high energy CPC injector based on the plasma vacuum field accelerator. This shows the plasma vacuum field acceleration the principle. This one has a huge gradient and about 100 GB per meter. So this is overall is conceptually designed for the CPC injector. This one is using this existing as the CPC injector 10 GB injector design to put to adding the plasma like 1 to get the 45 GB. Another scheme is using this shorter injector about 3.4 GB to adding as a plasma like 2 to get as a 45 GB. And this electron positron acceleration to 100 GB level in cascaded HTR PW vacuum field is acceleration with TR to 10. It's possible to get the 10 GB electron beam maybe it's to more than 100 GB. Jiwenzai has presented the CPC collider ring as SRF systems. The SRF parameters and the layout established in a field of high Higgs priority, low construction cost, and upgradability. So, okay, this is for the collider ring as SRF system is parameters. And this is a booster SRF systems. A booster is using as 1.3 gigahertz as a frequency. Its main ring is 650 as a megahertz as a frequency. The Sapong is presented some success of nitrogen doping research in IHAP. After the nitrogen doping, as a Q0 increases obviously at a low field for both as 600 megahertz, one shell as cavities. So this is a vertical test result of the 650 megahertz one shell cavities. This red line is the after nitrogen doping. And we developed as 650 megahertz two-cell cavities. This is two-cell cavities for the vertical testing. We got the vertical result it's about 4 to 10 to 10 at about 20 megawatt per meter, which is close to the CPC target. CPC target 4 to 10 to 10 at 22 megawatt per meter in here. As the next is to where the CPC target will be achieved by using nitrogen doping and EP. This one as a result is EP. We are going to construct build as the test for the two cavity as the current module for the 650 cavities. And this one is almost to completed the designing. And for the high efficiency the collection R&D, we are now in this stage, and we are nearly finalizing the mechanical design of the conventional efficiency, the high power collections. So in this year, we will be to start to fabrication of this 650 the high power collection. It's a conventional efficiency about 65. So next 3 years, we are going to develop more than the 80% efficiency is high power collections. So we are going to test high power test in about 2021. We hope to get more than 80% of the high efficiency. This is we are almost completed the mechanical designing for the conventional efficiency collection. So we now maybe this year we're going to fabrication. Yang Mei has presented some designing of the CPC collider ring. There's a dual as a dipole magnet, and the dual as cosipole magnet, and the single as a positive sexpole magnet. And the designing of the booster magnet. The booster magnet has the difficulties is the very low is the field. Its lowest field is about 31 Gauss, and the highest the field is about 400 Gauss. So we are going to research make R&D for the using ion-dominated frame, and another one is hollow coil as frame. Maybe as this hollow coil as a frame is impossible because of we cannot get this high. Very big, it's large as the how does this range of the magnetic field. So this one is the report from the sun. The low power as a low cost the designing of for FCC magnet. There's doing a twin dipole as a design, and they are developed first 1 meter as a prototype. And the twin is a quad design for the power saving about 25 megawatt at 170 GB, with is a copper as a conductor. This is for first 1 meter as a prototype. And for CPC vacuum as a design consideration for the CPC vacuum system, we are going to developing these positron ring as a copper as a vacuum chamber, using as a drawing as a mechanism. So electron ring as we are still using it is the aluminum vacuum chamber. And we are going to developing the RF shielding bellow so to allow the thermal expansion of the chambers and reduce the impedance of the vacuum chamber. We are also going to using the neg coating of the inside of the chamber. And now as for the high energy photon cells as test facility, we already to develop the neg coating. Neg coating has reached the project as the goals. The film lifetimes with the thickness of 100 nanometer will be experimented. And this one is FCC arc vacuum prototyping and integration. So the chambers features the lamp that's synchronous radiation absorbers with neg pumps, and the construction of the chamber prototype in the coming months, and the integration with twin magnet. So this is a bellow for supporting the chamber. Accelerator as a component for high current operation. The high beam is current. The current is a source of the heating as a discharging as established, and the degradation of the beam quality. So one of the main important ingredients to reach this result was the stable collision of the very intense multi-bunches beams. This has become possible due to the careful design of the low impedance, vacuum chambers components, and devices to cope with beam instabilities. This is presented by Sopong Lee as for consideration of the CPC cryogenics. CPC have 4 cryogenic stations. This is 2, this is 2. And the refrigeration is about 4 times 18 kilowatt. It is 4.4 Kelvin. For the CPC power consumption, this is presented by Wade and Zhou. The CPC now is the power consumption is calculation is about 266 and by CDR. So the wall plug efficiency very high, is in the 23%. And up to now in the world, just such as a machine cannot get so high as efficiency, the wall plug efficiency about as it seems to be less than 20%. So this one is the FCC as a power consumption about 308 megawatt. The fusion colliders is either circular or linear. It requires 100 megawatt power. The required wall plug efficiency is to 23% for the CPC. And the innovative thinking and ideas, this is very high. So how to decrease this wall plug efficiency is very important. For the high temperature magnet solenoid, the applied high temperature superconductor collaboration that formed in October 2016, including 18 institutions and companies in China. The goal is to increase the iron-based superconductor and Revico and 2212. So the magnet and SLB cavities. And this is a working group. It's fundamental science study, and IBS as conductor R&D, and etc. So the proposal for the strategic priority research program of the Chinese Academy of Sciences already is proposed. So now it's ranked number 1 in 7 candidates by academic committee of the Chinese Academy of Sciences. So we developed 12 Tesla twin aperture dipole magnet, and the first test result of the first high field dipole magnet in China in February this year. This is a testing result of 10.2 Tesla at 4.2 Kelvin. Next step is to replace niobium titanium coil with the new niobium 3 tin coils, and insert the IBS coils to test the high field performances. Yeah. This one is the worldwide FCC as an niobium 3 tin as a program, including several countries and several country companies. So maybe I have as one of this collaboration. So this is a 16 dipole test design activities and options. So there's several institutions, and the short model magnet has 1.0 millimeter length will be built from the 18 to 22. And this is a 15 Tesla dipole demonstrator in the United States. And this is a 16 Tesla as a ERMC as a construction at the Sun. So thank you, all speakers, and thanks for your attention.
Any comments or other questions? Anything? No? Okay, thank you.
Okay, thank you.